Welcome to the end of the world. Hey guys, welcome back. Tonight we're doing something a little different. I hope you've got your pillows fluffed and your lights dimmed, because we're about to spend the next couple hours talking about the single worst day in the history of life on Earth. And I mean that literally, not metaphorically worst. Actually, genuinely, the worst day ever. The day a rock from space decided to ruin everything. Now, I know what you're thinking. Dinosaurs, asteroid, boom, dead. We all learned this in like 4th grade. But here's the thing. Most people don't actually know what happened on that day. Not really. Not the specifics. Not the horrifying, drawn-out, absolutely devastating specifics. And that's what we're here for tonight. Because this isn't just a story about extinction. It's a story about a single moment that changed everything, and then kept changing everything for months and years afterward. So get comfortable. Maybe grab some tea. Because we're going back 66 million years to the Yucatan Peninsula, to a day that started out perfectly normal and ended with 99.99% of all living things on Earth either dead or dying. Fun stuff. Relaxing content. Let's begin. It's a Tuesday. Well, not really, because the concept of Tuesday won't exist for another 65,999,000 years or so. But let's just say it's a Tuesday, because if the world's going to end, it might as well be a Tuesday. Tuesdays have that vibe. It's late spring, probably, or early summer. The exact season doesn't matter much, because the climate is warm and humid pretty much everywhere. Earth in the late Cretaceous is a greenhouse planet. There's no ice at the poles. Sea levels are high. Temperatures are balmy. If you were a dinosaur, this is basically paradise. Which is convenient, because you are a dinosaur. Most things are dinosaurs. The sun rises over what will one day be called the Gulf of Mexico. But right now, it's just a shallow, warm sea full of ammonites and mosasaurs and other things with too many teeth. On the coastline, in the lowland forests, a herd of Alamosaurus, these massive, long-necked sauropods, are doing what they do best, which is eating. Just eating, constantly. They're like living construction cranes with digestive systems. Each one weighs about 70 tons. They don't have natural predators because nothing alive is stupid enough to try and kill something that size. They're basically unkillable. Spoiler alert, they're all going to be dead by dinner time. But they don't know that yet. Right now, they're just munching on ferns and conifers, completely oblivious. Nearby, a pack of smaller theropods, maybe some kind of dromaeosaur, are squabbling over a carcass. There's a lot of hissing and posturing involved. Dinosaurs are dramatic. Further inland, a herd of triceratops are grazing. They're basically the buffalo of the Cretaceous. Everywhere you look, there's a triceratops. They're doing fine. They've been doing fine for millions of years. In the forests, smaller dinosaurs are going about their business. Birds, because yes, birds are already a thing, birds are just small feathered dinosaurs that figured out how to fly, are singing in the trees. Mammals, tiny and nervous, and mostly nocturnal, are hiding in burrows. Mammals in the Cretaceous are not impressive. They're basically rat-sized insect eaters that spend most of their time being terrified of everything. Which, to be fair, is a reasonable survival strategy when you share the planet with tyrannosaurs. Everything is fine. Everything is normal. It's just another day in the late Cretaceous, and life is doing what life does. Growing, eating, reproducing, dying. The usual cycle. And then, at approximately 10:30 in the morning, again, not really, but let's say 10:30, because it makes the story easier to follow, something appears in the sky. Now, here's the thing about asteroids. Most of them miss. Space is big. Really, really big. And Earth, in the grand scheme of things, is tiny. It's a little blue marble spinning through an incomprehensible void, and the odds of any given space rock actually hitting it are astronomically small. Pun intended. But sometimes the math doesn't work out in your favor. The object that is currently screaming toward Earth at about 20 kilometers per second, that's roughly 45,000 miles per hour if you prefer your doom in imperial units, is not technically an asteroid. It's probably a comet, or maybe a piece of a comet that broke off from something bigger. Scientists argue about this. The distinction doesn't really matter, though, because either way, it's a rock the size of a mountain, and it's about to hit the planet like a cosmic baseball bat. It's about 10 to 12 kilometers across. That's 6 to 7 miles for the Americans in the audience. To put that in perspective, Mount Everest is about 9 kilometers tall. This thing is bigger than Everest, and it's moving fast. Faster than anything has ever moved in Earth's atmosphere. Faster than comprehension, really. As it enters the upper atmosphere, it starts to heat up. The air in front of it compresses so violently that it becomes plasma. The object itself begins to glow. Not like a shooting star. Shooting stars are tiny, barely the size of a pebble, and they burn up harmlessly. This thing is not burning up. This thing is a bullet fired by the universe, and Earth is standing directly in front of the gun. From the ground, if you happen to be looking up, and let's say you're a dinosaur, so you don't really have the cognitive framework to understand what you're seeing, it would look like a second sun suddenly appearing in the sky. Bright, blinding, getting bigger. And it's completely silent. Sound travels at about 300 meters per second. The asteroid is traveling at 20,000 meters per second. It's moving so fast that it's outrunning its own sound. So if you're not on the ground watching this thing approach, you don't hear anything. You just see this impossibly bright light getting closer and closer, and your tiny dinosaur brain is trying to process what's happening. But there's no frame of reference. Nothing in your evolutionary history has prepared you for this. And then it hits.
The impact site is in the Yucatan Peninsula, in what is now Mexico. Specifically, it's near a town that won't exist for 66 million years called Chicxulub. The asteroid, let's just call it an asteroid, even though it's probably a comet, because asteroid is faster to say, slams into a shallow tropical sea at a slight angle, maybe 20 to 30 degrees from vertical. The energy released is unfathomable. Estimates put it at about 100 million megatons of TNT. To put that in perspective, the most powerful nuclear weapon ever detonated, the Tsar Bomba, was 50 megatons. This impact is 2 million times more powerful than the Tsar Bomba. It's roughly equivalent to all the world's nuclear arsenals going off at once, multiplied by 1,000, and then set on fire. The asteroid punches through the shallow sea in less than a second. It doesn't even slow down. Water might as well be air. Then it hits the seafloor. Then it hits the bedrock. Then it just keeps going. It excavates a crater about 30 kilometers deep in roughly 2 seconds. 30 kilometers. That's deeper than the Earth's crust in most places. The asteroid itself is vaporized on impact. Just gone, turned into superheated gas and plasma. But the energy has to go somewhere, and it goes into the ground. The bedrock shatters, not breaks, shatters. Rock that has been solid for hundreds of millions of years suddenly behaves like liquid. The entire impact site turns into a temporary sea of molten stone. The crater begins to form, expanding outward at supersonic speeds. And here's where it gets worse. Because the Yucatan Peninsula, as it turns out, is largely made of limestone, and limestone is made of calcium carbonate. And when you superheat calcium carbonate, it releases carbon dioxide. Lots of carbon dioxide. So now, in addition to everything else, the impact is releasing trillions of tons of greenhouse gases directly into the atmosphere. But we're getting ahead of ourselves. Let's stay in the moment. Let's talk about what happens in the first few seconds. The shock wave from the impact moves outward at several kilometers per second. Not sound, not wind, a shock wave. A wall of compressed air and vaporized rock traveling faster than the speed of sound. Everything within a few hundred kilometers of the impact site is simply erased. Forests, dinosaurs, oceans, it doesn't matter. It's all gone in an instant, vaporized, turned into plasma, and scattered into the atmosphere. But the shockwave doesn't stop there. It keeps going, expanding outward like a ripple on a pond, except this ripple is made of superheated gas and pulverized rock, and it's moving at hypersonic speeds. At 500 kilometers from the impact, the shockwave is still strong enough to level entire forests. Trees that have stood for centuries are snapped like toothpicks and blown away. Any animal unlucky enough to be above ground is killed instantly. Not by the heat, not by debris, just by the sheer force of the air pressure. Their lungs collapse, their eardrums rupture. They're dead before they even know what's happening. At 1,000 kilometers, the shockwave is weaker but still devastating. Animals are thrown through the air. The ground shakes so violently that it cracks. Fissures open up in the earth. Landslides start on every hillside. And this is all happening in the first 10 seconds. Meanwhile, back at the impact site, the crater is still forming. The bedrock, liquefied by the impact, is rebounding. It's called isostatic rebound, and it's what happens when you punch a hole in something elastic. The ground literally bounces back. A central peak begins to form in the middle of the crater, rising up like a slow-motion fountain made of molten rock. It climbs to a height of several kilometers, then collapses back down, creating a ring of mountains around the crater rim. The final crater is about 150 kilometers across. That's nearly 100 miles. You could fit the entire island of Hawaii inside it with room to spare. And it's surrounded by a ring of mountains taller than the Rockies, all created in less than 10 minutes. But here's the thing. The crater is just the impact site. The real damage is what happens next. Let's talk about the ejecta. When the asteroid hit, it didn't just make a hole. It threw stuff into the air. Lots of stuff. Trillions of tons of stuff. Rock, vaporized seawater, bits of asteroid, molten droplets of stone, it all goes up. Some of it goes straight up. Some of it goes sideways, and some of it goes up so fast that it escapes the atmosphere entirely and goes into orbit. We're talking about rocks the size of cars being thrown into space, and they don't just float there. What goes up must come down, and when it comes down everywhere. Within minutes, fragments of the Yucatan Peninsula are raining down across North America. Glowing chunks of molten rock streaking through the sky like meteors. Except they're not meteors, they're pieces of Earth, superheated to thousands of degrees, falling back to the surface at terminal velocity. Imagine standing in a forest in what will one day be Montana. You're a dinosaur, maybe a hadrosaur, one of those duck-billed herbivores. You're having a pretty good day. The sun is shining, there's plenty of food, and then, suddenly, the sky starts to glow. Not like sunset, not like fire, like the sky itself is turning into an oven. You look up, and you see thousands of streaks of light all falling at once. The air starts to heat up, not gradually, instantly. The temperature rises 10 degrees, 20 degrees, 30 degrees. In a matter of minutes, the air temperature across North America climbs to over 300 degrees Celsius. That's hot enough to boil water, hot enough to ignite wood. And that's exactly what happens. The forests catch fire. Not some of the forests, all of the forests. Every tree within line of sight of the sky spontaneously ignites. It's called thermal radiation. And it's the same thing that happens if you stand too close to an open flame, except the flame in this case is the entire sky. So now, if you're that hadrosaur in Montana, you're on fire. The ground is on fire. The trees are on fire. Everything is on fire. And you can't run because there's nowhere to run to. The fires are everywhere. The entire continent is burning. And this is still within the first hour. Let's check in with our friends on the coast, the Alamosaurus herd. Remember them? They're about 2,000 kilometers from the impact site, far enough that they didn't get vaporized by the initial shockwave. Lucky them. But they're not lucky for long.
Because the impact didn't just create a shockwave in the air, it also created a shockwave in the water. And when you drop a mountain-sized object into a shallow sea at 45,000 miles per hour, you create what is technically called a tsunami, but which would be more accurately described as a wall of water tall enough to drown a skyscraper. The initial wave is about 1.5 kilometers tall. That's almost a mile. A mile-high wall of water moving at the speed of a jet plane, radiating outward from the impact site in all directions. It takes about 15 minutes for the wave to reach the coastline where our Alamosaurus herd is grazing. They probably feel the ground shaking first. Maybe they look up. Maybe they see the water receding from the shore, which is what happens right before a tsunami hits, because the wave pulls all the coastal water back with it, like someone inhaling before a scream. And then the wave arrives. It doesn't crash. It doesn't break. It just rolls over the land like a steamroller made of ocean. Everything in its path is swept away. Trees, rocks, dinosaurs, it doesn't matter how big you are or how heavy you are. A 70-ton Alamosaurus is nothing compared to 1 trillion gallons of water moving at hundreds of miles per hour. The wave travels inland for hundreds of kilometers before it finally runs out of momentum. And when the water recedes, because it has to recede eventually, that's how waves work, it drags everything back with it. The coastline is scoured clean, stripped down to bedrock. Every living thing is gone. And the wave doesn't just hit the Gulf Coast, it hits every coast. The tsunami radiates outward across the entire planet. It crosses the Atlantic. It crosses the Pacific. Coastlines on the other side of the world are hit by waves hundreds of feet tall. Islands disappear. Shallow seas slosh back and forth like water in a bathtub. Mosasaurs, the giant marine reptiles that have ruled the oceans for millions of years, are thrown onto dry land and left to suffocate. Ammonites, those spiral-shelled cephalopods that have existed since the Paleozoic, are smashed against rocks and shattered into fragments. In the space of an hour, the oceans have become a chaotic, churning nightmare. But wait, it gets worse. Because while the forests are burning and the coasts are drowning, something else is happening in the atmosphere. Remember all that ejecta we talked about? The trillions of tons of vaporized rock and molten debris that got thrown into the air? Well, some of it went into orbit, and now it's coming back down. But it's not coming back down gently. It's coming back down at orbital velocity, which is about 25,000 kilometers per hour. And when something enters the atmosphere at that speed, it heats up a lot. So now, the upper atmosphere is full of glowing, superheated debris, all falling back to Earth at the same time. And as it falls, it radiates heat. Infrared radiation, thermal radiation, the kind of radiation you feel when you stand in front of a fire. Except this fire is global. The sky is literally glowing. If you're anywhere on the planet with a clear view of the sky, it looks like the heavens are on fire. And the heat is intense. Intense enough to ignite anything flammable on the ground. So now the entire planet is experiencing wildfires, not just North America, everywhere. Europe, Asia, South America, Africa. Every forest, every grassland, every ecosystem with plant life is burning. Animals underground, burrowing mammals, reptiles, and amphibians have a chance. They're insulated from the heat. But anything above ground is cooked, literally. The air temperature rises to oven-like levels. Dinosaurs die from heat stroke before they even reach the flames. And the fires burn for hours, days in some places. The entire planet is wrapped in a blanket of smoke and ash. By the end of the first day, an estimated 75% of all land-based life is dead. But the worst is yet to come.
The long darkness. Okay, so let's take stock of where we are. It's been about 24 hours since the impact. The initial shockwave has circled the globe multiple times, weakening each time, but still strong enough to shatter windows, if windows existed, which they don't, because glass won't be invented for another 65 million years. The wildfires are starting to die down, mostly because there's nothing left to burn. The tsunamis have receded, leaving coastlines that look like they've been sandblasted. The air is full of smoke and dust and vaporized rock. The sky, which was glowing red-hot just a few hours ago, is now dark. Not night dark, darker than that. Apocalypse dark. The sun is gone. Not literally gone, obviously. The sun is still there, 93 million miles away, doing its thing. But you can't see it anymore, because between you and the sun is a cloud of debris so thick, so dense, that no sunlight can penetrate it. This is called an impact winter, and it's going to last for years. Let's talk about what that means. Photosynthesis. You remember photosynthesis, right? That thing where plants use sunlight to make food? The entire basis of pretty much every food chain on the planet? Yeah, that's not happening anymore. Because there's no sunlight. Plants need light. It's not optional. It's literally how they survive. They take sunlight, combine it with carbon dioxide and water, and turn it into glucose and oxygen. It's the most important chemical reaction in the history of life, and it just stopped. Within days, plants start to die. Not all of them, not immediately. Some plants can survive for a while without light. They have stored energy in their roots and tubers. Some seeds can go dormant and wait out bad conditions. But the vast majority of plant life, dead within weeks. And when the plants die, everything that eats plants dies. Remember those triceratops we mentioned earlier? The ones that were everywhere? They're herbivores. They eat plants, lots of plants. A single triceratops needs to eat hundreds of pounds of vegetation every day just to maintain its body weight. And now there are no plants. They starve. It takes a while. A triceratops is big enough that it can survive for a few weeks without food, maybe even a month or two if it's lucky. But eventually, the stored fat runs out. The muscles start to break down. The animal gets weaker, slower. Eventually, it just lies down and doesn't get back up. And it's not just triceratops. It's all the herbivores. The hadrosaurs, the ankylosaurs, the ceratopsians, the sauropods. Every single plant-eating dinosaur on the planet is starving to death. You might think, okay, well, what about the carnivores? They eat meat, not plants. They should be fine, right? Wrong. Because the carnivores eat the herbivores. And when the herbivores die out, the carnivores have nothing to eat either. Sure, they can scavenge for a while. There are a lot of dead herbivores lying around. But scavenging only works if there's something to scavenge. And after a few months, all the herbivore corpses are gone, picked clean by scavengers or rotted away or buried under ash. And then the carnivores start to starve too. Tyrannosaurus rex, Albertosaurus, Dromaeosaurus, every predator on the planet, from the massive apex predators to the small opportunistic hunters, is running out of food. Some of them turn to cannibalism. There's evidence of this in the fossil record, bite marks on tyrannosaur bones that match tyrannosaur teeth. They're eating each other, because what else is there to eat? But cannibalism doesn't solve the problem. It just delays it. You can't sustain a population by eating itself. The math doesn't work. Eventually, the carnivores die too. Within 6 months of the impact, Most of the large dinosaurs are gone. Let's talk about the ocean, because the ocean is having an equally bad time. The base of the oceanic food chain is phytoplankton, microscopic algae that float near the surface and photosynthesize. They're the ocean's equivalent of grass. Everything eats them, either directly or indirectly. Fish eat zooplankton, which eat phytoplankton. Bigger fish eat smaller fish. Marine reptiles eat bigger fish. It's a nice, neat food chain. Except the phytoplankton are dying. Because again, no sunlight. Phytoplankton need light just as much as plants do. More, actually, because they live in water, which absorbs light. They need to stay near the surface where the sun is brightest. But now there is no bright sun. There's just darkness. The phytoplankton die within days, and when they die, they sink. Trillions upon trillions of dead microorganisms drifting down through the water column, settling on the ocean floor like snow. Except this snow is made of corpses, and it's covering everything. The zooplankton, which depend on the phytoplankton, starve. The fish that eat the zooplankton starve. The bigger fish starve. The marine reptiles, the mosasaurs, the plesiosaurs, the sea turtles, starve. Ammonites, those beautiful spiral-shelled cephalopods that have survived every mass extinction for the past 300 million years, finally meet their end. Not from predators, not from disease, from starvation. Their food source is gone, and they can't adapt fast enough. The oceans become a graveyard. And here's the thing about ocean graveyards. They don't just affect the ocean. They affect the whole planet. Because when all those dead organisms sink to the bottom and decompose, they use up oxygen. Bacterial decomposition is an oxygen-intensive process. And when you have trillions of tons of organic matter all decaying at once, the oxygen levels in the water plummet. This creates what's called anoxia, oxygen-depleted water. And when water becomes anoxic, nothing can live in it. Not fish, not invertebrates, not even most bacteria. So now, even the animals that somehow survived the initial die-off are suffocating. The oceans, which covered 70% of the planet's surface and supported an incomprehensible diversity of life, are now dead zones.
Meanwhile, back on land, let's check in with the survivors. Because there are survivors. Not many, but some. Small animals, mostly. Things that lived underground or underwater or in other protected environments. Mammals, for instance. Those tiny, rat-sized insect eaters we mentioned earlier, some of them make it. Because they lived in burrows, which protected them from the initial heat pulse. And because they were small, they didn't need much food. A few insects, some seeds, maybe some carrion, that was enough to keep them alive. Crocodiles and alligators also survive, which honestly is not surprising. Crocodilians are nearly unkillable. They can go months without eating, they can survive in both fresh and salt water, they can regulate their body temperature by basking or hiding. They're basically living tanks. Of course they survive the apocalypse. Some birds make it too. Not all birds. The big flightless ones, the ones that couldn't escape the fires or find shelter, they're gone. But some of the smaller, more adaptable birds survive. Probably shorebirds, scavengers, the ones that could eat whatever was available and didn't need a specific habitat. Turtles and tortoises do okay, relatively speaking. They can retreat into their shells for protection, and they don't need to eat much. Some lizards and snakes make it, especially the ones that could burrow or hide in rock crevices. Amphibians, frogs, salamanders have a mixed survival rate. Some of them make it, especially the ones that lived in water or underground. But a lot of them die because amphibians have permeable skin and are really sensitive to environmental changes. Fish in freshwater systems have a better survival rate than marine fish because freshwater ecosystems are more isolated. A river or lake can maintain its own food chain for a while, even if the ocean is dying. Some fish can eat detritus or algae that grows in low light conditions. They're not thriving, but they're alive. And insects? Insects are doing fine. Well, not fine. A lot of them died. But insects have short lifespans and reproduce quickly, which means they can adapt faster. And they're small, which means they don't need much food. And they eat basically anything. Dead plants, dead animals, fungus, each other. Insects are the ultimate survivors. So the planet after the impact is basically a world ruled by rats, crocodiles, and cockroaches. Which, to be honest, sounds about right. Let's talk about the climate, because things are about to get even worse. Remember all that carbon dioxide that got released when the limestone vaporized? And all the soot and ash from the wildfires? All of that is now in the atmosphere, and it's causing problems. First, there's the immediate cooling effect. All that ash and dust in the air is blocking sunlight, which means the planet is getting colder, a lot colder. Temperatures drop by 10 to 15 degrees Celsius globally. In some places, it drops even more. This is bad for anything that's cold-blooded. Reptiles, amphibians, insects. They all rely on external heat sources to regulate their body temperature. And when the temperature drops, they become sluggish. They can't hunt. They can't escape predators. They can't even digest food properly. So even the animals that survived the fires and the starvation are now dying from hypothermia. But here's where it gets really ironic. Because eventually the dust settles. It has to. Gravity is a thing. The particles in the atmosphere slowly fall back to Earth, pulled down by their own weight. And after a few years, maybe a decade, maybe two, the sky clears. The sun comes back. And you'd think that would be good news, right? Sunlight returns, plants can start growing again, the food chain can rebuild itself. Happy ending. Except it's not a happy ending. Because now all that carbon dioxide, the stuff that was released during the impact, is still in the atmosphere. And carbon dioxide is a greenhouse gas. So now, instead of being too cold, the planet starts to get too hot. This is called a greenhouse spike, and it's brutal. Temperatures rise by 5 to 10 degrees Celsius above pre-impact levels. The poles, which were already ice-free, become tropical. The equator becomes unbearable. Heat waves sweep across the continents, droughts become common. And the plants that managed to survive the impact winter, a lot of them can't handle the heat spike too. They die too. So you've got this 1-2 punch of climate catastrophe. First, everything freezes, then everything burns. And the few species that manage to survive one extreme can't survive the other. It's not fair. But extinction events aren't fair. That's kind of the point. Let's take a moment to talk about what the world looks like at this point. It's been maybe 2 or 3 years since the impact. The sky is clear again, the fires are long since burned out, the tsunamis are ancient history. But the planet is unrecognizable. The forests are gone, just gone. In their place are vast, empty plains covered in ferns and moss and low-growing shrubs. Ferns do well in post-apocalyptic landscapes because they reproduce by spores, which can survive harsh conditions. So the early post-impact world is basically just ferns. Ferns everywhere. It's called a fern spike in the fossil record, and it's one of the markers scientists use to identify the extinction layer. The rivers and lakes are full of algae and bacteria. The water is murky and green. There are some fish, but not many, mostly small, hardy species that can tolerate low oxygen levels. The oceans are still mostly dead. It's going to take thousands of years for marine ecosystems to recover, maybe tens of thousands of years. And the land is quiet. Eerily quiet. Because most of the animals are gone. There are no dinosaur calls echoing through the valleys. No herds of ceratopsians thundering across the plains. No pterosaurs circling overhead. The sky is empty. The ground is still. If you could somehow visit Earth at this moment, the most striking thing wouldn't be the devastation. It would be the silence. Because Earth, for the first time in hundreds of millions of years, is a planet without dinosaurs.
The survivors and the aftermath. So here we are, 3 years after the impact. Maybe 5? Time gets a little fuzzy in the fossil record, and honestly, when you're living through an extinction event, you're probably not keeping a detailed calendar. The planet is starting to stabilize. Sort of. The dust has settled, the fires are out, the tsunamis are over. The temperature is still swinging between too cold and too hot, but at least it's not swinging as wildly as it was right after the impact. And life, because life is stubborn and refuses to die no matter how hard the universe tries, is starting to come back. Not the same life, obviously. The dinosaurs are gone, the pterosaurs are gone, the marine reptiles are gone, the ammonites are gone. About 75% of all species on Earth are extinct. The ecosystems that existed before the impact have been completely dismantled. But the survivors are still here, and they're about to inherit the Earth. Let's talk about mammals. Mammals before the impact were, to put it gently, not impressive. They'd been around for about 160 million years at this point, but they'd spent most of that time being small and nervous and nocturnal, living in the shadow of the dinosaurs, eating insects and seeds, and trying very hard not to get stepped on. The largest mammal in the late Cretaceous was probably about the size of a badger. Most of them were smaller, mouse-sized, shrew-sized. They had fur, and they were warm-blooded, and they nursed their young, which were all evolutionary advantages, but none of that mattered much when there was a Tyrannosaurus rex around. But now the Tyrannosaurus is gone, and the Triceratops is gone, and all the other dinosaurs are gone, which means all those ecological niches, herbivore, carnivore, omnivore, insectivore, are suddenly empty. And mammals, being opportunistic little survivors, start to fill them. It doesn't happen overnight. Evolution doesn't work that fast. But over the course of a few thousand years, which is basically overnight in geological terms, mammals start to diversify. They get bigger. They develop new diets. They adapt to new environments. Within a few 100,000 years, there are mammals the size of dogs, then the size of wolves. Eventually, a few million years down the line, there are mammals the size of elephants. But we're getting ahead of ourselves. Right now, in the immediate aftermath of the impact, mammals are still small and scrappy. They're eating whatever they can find: seeds, insects, carrion, roots, fungus. They're not picky. They can't afford to be. And that adaptability is their greatest strength, because in a world where the most of the food chains have collapsed, the animals that can eat anything are the ones that survive. Birds are also doing well, or at least some birds are. The ones that survived the impact were mostly ground-dwelling birds, shorebirds, scavengers, the kinds of birds that didn't need a specific habitat or a specific food source. They could eat seeds, insects, carrion, whatever was available. And now, with the skies empty of pterosaurs, birds have a new opportunity. They start to diversify. They get bigger. Some of them lose the ability to fly and become terrestrial predators. Others develop specialized beaks for cracking seeds or catching fish. Within a few million years, there are giant flightless birds, forest harids, also known as terra birds, that stand 10 feet tall and hunt mammals. They're basically the dinosaurs' revenge, evolution's way of saying, "You thought you got rid of us? Think again." But again, we're jumping ahead. Right now, birds are just small, opportunistic survivors, pecking through the ashes and trying to find enough food to make it through the winter. Crocodilians, as mentioned earlier, are doing fine. They're always fine. Crocodiles have survived every major extinction event in Earth's history. They survived the Permian extinction, which killed 90% of all life. They survived the Triassic extinction. They survived the Cretaceous extinction. They'll probably survive the next one too, whatever that is. Crocodiles are basically nature's middle finger to catastrophe. They're not thriving, exactly. The oceans are still in rough shape, which means marine crocodiles are struggling. But the freshwater crocodiles, the ones that live in rivers and swamps, are doing okay. They can eat fish, turtles, small mammals, birds, basically anything that comes near the water. And they can go months without eating if they have to. So yeah, crocodiles are fine. They're always fine. fish are slowly recovering. The freshwater fish, anyway. Marine fish are still in trouble because the ocean ecosystems are still devastated. But rivers and lakes are more isolated, and they recover faster. Algae starts to grow again. Insects lay eggs in the water. Fish eat the insects. Bigger fish eat the smaller fish. The food chain starts to rebuild itself. It's fragile. It's precarious. But it's happening. And in a few thousand years, the oceans will start to recover too. Slowly. Very slowly. But recovery is possible. Let's talk about plants, because plants are the key to everything. Without plants, there's no food chain. Without plants, there's no oxygen. Without plants, there's no life. And for a while, it looked like plants might not make it. The impact winter killed most of them. The heat spike killed more. The soil was poisoned with ash and sulfur. The climate was unstable. But plants, like all life, are stubborn. Ferns come back first. They're tough. They can grow in poor soil. They reproduce quickly. Within a few years, the continents are covered in ferns. Then mosses and lichens appear. They help break down the ash and rocks, slowly rebuilding the soil. Then grasses start to grow. Not the kind of grass you're thinking of. Modern grass won't evolve for another 60 million years. But primitive grasses, low-growing, fast-spreading plants that can colonize disturbed ground. And then, slowly, the trees come back. Not the same trees, obviously. The forests of the Cretaceous are gone. But new forests grow to replace them. Different species, different ecosystems. And as the plants come back, so do the herbivores. Small mammals start eating the grass and the seeds and the leaves, which means predators have something to hunt, which means scavengers have something to scavenge. The food chain rebuilds itself, slowly, painfully, with a lot of false starts and dead ends, but it happens. Now you might be wondering, how long does this take? How long does it take for the planet to recover from a mass extinction? The answer is a long time. The immediate aftermath, the fires and the tsunamis and the impact winter, last for a few years, maybe a decade. The climate instability lasts for a few thousand years. The ecosystem recovery lasts for a few million years. It takes about 10 million years for biodiversity to return to pre-impact levels. 10 million years for the planet to fully heal. That's a long time. That's longer than the entire history of human civilization. That's longer than you can really comprehend. But from the planet's perspective, 10 million years is nothing. Earth is 4.5 billion years old. 10 million years is less than 1% of its history. It's a rounding error. The planet doesn't care about the extinction. The planet doesn't even notice. But the life that lived through it, that life cares. That life noticed. Let's talk about what gets lost. People tend to focus on the dinosaurs when they talk about the end Cretaceous extinction. And yeah, the dinosaurs are a big deal. They ruled the planet for 160 million years. They were the dominant life form on every continent. And then they were gone. But they weren't the only ones. Pterosaurs, flying reptiles that had existed since the Triassic, gone. Mosasaurs, giant marine reptiles that ruled the oceans, gone. Plesiosaurs, long-necked marine reptiles, gone. Ammonites, shelled cephalopods that had survived for 300 million years, gone. Uncountable species of fish, insects, plants, and microorganisms, gone. Entire ecosystems, gone. And here's the thing, we don't even know what those ecosystems looked like. We have fragments, fossils, trace evidence, but we can't recreate them. We can't see what was lost because it's too far in the past. The late Cretaceous was a world that was completely alien to us. The continents were in different places. The climate was different. The atmosphere was different. The life was different. And it's gone forever. No amount of scientific study can bring it back. No amount of fossil hunting can recreate what was lost. The dinosaurs are extinct, and extinction is permanent.
The science and the discovery. All right, let's fast forward a bit. 66 million years. That's how long it takes to get from the crater in the Yucatan to a group of scientists standing in a lecture hall arguing about geology. Because here's the thing, humans didn't always know about the asteroid. For most of human history, we didn't even know dinosaurs existed. We found their bones occasionally, giant bones buried in rock, and we made up stories about them. Dragons, giants, monsters. We didn't understand what we were looking at. It wasn't until the early 1800s that scientists started to realize these bones belonged to extinct reptiles. And even then, it took decades of arguing before everyone agreed on what to call them. Dinosaurs, terrible lizards, coined in 1842 by Richard Owen, who was brilliant, but also kind of a jerk. But that's a different story. For a long time, scientists thought dinosaurs just died out gradually. They got slower, stupider, less adapted to their environment. The climate changed, the mammals took over, and the dinosaurs faded away. A slow, gentle decline. Except that's not what happened at all. The breakthrough came in 1980. A geologist named Walter Alvarez was studying rock layers in Italy, specifically a thin layer of clay that marked the boundary between the Cretaceous and the Paleogene periods, the KPG boundary, they call it. The K is for Cretaceous because C was already taken by the Carboniferous period. Geology is confusing. Anyway, Alvarez noticed something weird about this clay layer. It was enriched with iridium. Now, iridium is a rare element on Earth's surface. It's usually found deep in the planet's core, or it comes from space. Meteorites have a lot of iridium, but Earth's crust, not so much. So Alvarez was like, that's weird. Why is there so much iridium in this layer? He brought the samples to his father, Luis Alvarez, who was a physicist, Nobel Prize winner, very smart guy. And Luis was like, well, if there's iridium in this layer, and iridium comes from space, maybe something from space hit the Earth at this point in time. And Alvarez was like, Dad, that's insane. And Luis was like, is it though? So they published a paper in 1980 proposing that a massive asteroid impact caused the extinction of the dinosaurs, and the scientific community lost its mind. See, the problem was that geologists at the time were not fans of catastrophism. Catastrophism is the idea that Earth's history is shaped by sudden, violent events, asteroid impacts, volcanic eruptions, floods, that kind of thing. The prevailing theory was uniformitarianism, the idea that Earth's history is shaped by slow, gradual processes, erosion, sedimentation, mountain building over millions of years, nice, predictable geology. And here come the Alvarezes saying, actually, a giant rock fell from space and killed everything. A lot of scientists thought it was ridiculous. They said the iridium could have come from volcanic eruptions, or it could have been deposited slowly over time, or it could be a measurement error. Maybe the Alvarezes didn't know how to use their equipment properly. There was a lot of skepticism, a lot of pushback. But then other scientists started finding the same iridium layer in Denmark, in New Zealand, in the United States, all over the world, right at the KPG boundary, always in the same thin layer of clay. So the iridium was real, but that still didn't prove there was an impact. For that, they needed to find the crater. Finding a 66 million year old crater is not easy. First of all, it's old, really old. 66 million years is a long time for erosion and sedimentation to cover things up. The crater could be buried under miles of rock, or it could be at the bottom of the ocean, or it could have been destroyed by tectonic activity. Second, the crater is huge, 150 kilometers across. That's not the kind of thing you just stumble over. You need satellite imagery, seismic data, gravitational anomaly maps. You need serious resources. But scientists kept looking, and in 1991, they found it. The Chicxulub crater, named after a small town in the Yucatan Peninsula. It's buried under half a mile of sediment, but it's there, a massive, circular structure, exactly the right size and exactly the right age. They drilled into it. They found shocked quartz, which is a type of quartz that only forms under extreme pressure, like the pressure of an asteroid impact. They found tektites, which are glassy spheres created when rock is vaporized and then cools rapidly. They found melted rock. They found everything you'd expect to find at an impact site. The evidence was overwhelming. By the mid-1990s, the scientific consensus was clear. An asteroid hit the Yucatan 66 million years ago, and it caused a mass extinction. The dinosaurs didn't die out gradually. They were killed in a single day. But here's the thing about science. It's never settled. There's always more to learn, always more questions to ask. Like, was it really just the asteroid? Or were there other factors? Because around the same time as the impact, something else was happening. The Deccan Traps, a massive volcanic eruption in what is now India. And I mean massive. This wasn't a single volcano. This was a flood basalt event. Lava pouring out of the ground for hundreds of thousands of years, covering an area the size of France. And volcanic eruptions release gases. Sulfur dioxide, carbon dioxide, ash, all the same stuff that makes impact winters so deadly. So, some scientists argue that the dinosaurs were already in decline because of the Deccan Traps. The climate was already unstable, the ecosystems were already stressed, and then the asteroid hit, and that was the final straw. Other scientists argue that the Deccan Traps weren't a major factor. The eruptions lasted for hundreds of thousands of years, which means ecosystems would have had time to adapt. The asteroid, on the other hand, was instantaneous. No time to adapt, no time to evolve, just instant death. The debate is still ongoing, but most scientists agree that the asteroid was the primary cause. The Deccan Traps might have made things worse, but the impact is what did the real damage.
Let's talk about some of the more fascinating details that have emerged from studying the impact. For one thing, scientists have figured out the exact angle of impact, about 60 degrees from vertical. If it had hit straight down, the crater would have been deeper and narrower. If it had hit at a shallow angle, it would have been wider, and some of the asteroid might have skipped off the atmosphere. 60 degrees is basically the worst possible angle. It maximized the amount of debris thrown into the atmosphere. It maximized the energy transferred into the ground. It was like the universe carefully calculated the most destructive trajectory possible. Scientists have also figured out the exact time of year, late spring or early summer in the northern hemisphere. They know this because they found fossilized fish from the impact site with growth rings in their bones, like tree rings. And the rings indicate they died during a certain season. They've even figured out the time of day. The ejecta pattern suggests the asteroid hit in the late morning, around 10 or 11 a.m. local time. So we know, with a disturbing level of precision, exactly when and how the world ended. There's also been a lot of research into how long it took for life to come back. The first organisms to recolonize the impact site were bacteria and algae. They show up in the fossil record within a few years of the impact. tough little survivors. Ferns appear within a few decades, small mammals within a few centuries, but it takes about 30,000 years for forests to start growing back in the impact region. And it takes about 300,000 years for ecosystems to stabilize. That's not 10 million years. That's the time it takes for global biodiversity to recover. But local recovery happens much faster. Within a few 100,000 years, the impact site is green again. There are plants and animals and functioning ecosystems. Life bounces back. It always does. One of the haunting discoveries came in 2019, a site called Tanis in North Dakota. Tanis is a fossil bed that appears to preserve the immediate aftermath of the impact. We're talking hours, maybe a day. The site contains the fossils of fish with impact spherules, those glassy tektites we mentioned earlier, lodged in their gills. The fish were swimming when the ejecta started to fall, and they inhaled the spherules and died. There are also fossilized trees with their bark scorched by the thermal pulse, ammonites, a pterosaur, a partial triceratops, all jumbled together in a chaotic mass grave. The site appears to have been buried by a massive surge of water, possibly the Seiche wave caused by the impact. A seiche is like a standing wave in a body of water, and it can slosh back and forth for hours after an earthquake or impact. So the animals at Tanis were killed by falling ejecta, then buried by a wave, all within a few hours of the impact. It's a snapshot of the apocalypse, frozen in stone for 66 million years.
What it all means. So here we are. We've talked about the impact. We've talked about the extinction. We've talked about the recovery. We've talked about the science. But what does it all mean? Why does any of this matter? Well, for one thing, it matters because we're here. Humans exist because the dinosaurs died. If the asteroid hadn't hit, the dinosaurs would probably still be around. They were doing fine. They were diverse. They were adaptable. There's no reason to think they would have died out on their own. And if the dinosaurs were still around, mammals would still be small and insignificant. We wouldn't have evolved. Primates wouldn't have evolved. Humans wouldn't exist. So in a very real sense, we owe our existence to a random rock from space that happened to hit the Earth 66 million years ago. Which is kind of humbling when you think about it. But there's another reason it matters. Because the end Cretaceous extinction is a reminder that life on Earth is fragile. We like to think of ourselves as special, as permanent, as somehow exempt from the rules that govern the rest of nature. But we're not. Humans have been around for maybe 200,000 or 300,000 years, depending on how you define human. Dinosaurs were around for 160 million years, and they still went extinct. Nothing lasts forever. Not species, not ecosystems, not civilizations. The dinosaurs didn't do anything wrong. They weren't poorly adapted. They weren't evolutionarily inferior. They just got unlucky. A rock fell from the sky, and that was it. And the same thing could happen to us. Now, before you start panicking, let me reassure you, the odds of another dinosaur killer asteroid hitting Earth in our lifetime are extremely low. Astronomers are constantly scanning the sky for near-Earth objects, and they've cataloged most of the big ones. We'd have decades of warning if something that size was heading our way. But that doesn't mean we're safe. There are other existential threats: climate change, nuclear war, pandemics, artificial intelligence, supervolcanoes, gamma-ray bursts. The list goes on.
And the lesson of the end Cretaceous extinction is that catastrophe can happen. It has happened. It will happen again. The question is, are we prepared? The dinosaurs weren't prepared. They couldn't be. They didn't have telescopes, or satellites, or nuclear weapons. They couldn't see the asteroid coming, and they couldn't have stopped it if they did. But we can. We have the technology to detect asteroids. We have the technology to potentially deflect them. We have the ability to see threats coming and take action. We also have the ability to cause our own extinction through war, through pollution, through reckless use of technology. The dinosaurs were victims of chance, a random cosmic event that they had no control over. We, on the other hand, have control, which means we have responsibility. The extinction of the dinosaurs is a cautionary tale, not about asteroids specifically, but about the fragility of life, about how quickly things can change, about how a thriving, diverse planet can become a wasteland in a matter of days. And it's a reminder that we probably should take care of the planet we have, because we don't get another one. Let's talk about what comes next. Not for the dinosaurs, they're done, but for Earth, for life. Because the story doesn't end with the extinction. The story continues. Life continues. The mammals that survived the impact diversified. They evolved into thousands of new species. Some became tiny. Some became huge. Some learned to fly. Some returned to the ocean. Within 10 million years, there were bats and whales and primates. Within 20 million years, there were elephants and horses and cats and dogs. Within 65 million years, there were humans. And humans, for better or worse, inherited the earth. We're the descendants of those tiny, scrappy mammals that hid in burrows while the world burned. We're the product of 66 million years of evolution, all made possible by a random asteroid impact, which is pretty wild when you think about it. The dinosaurs are gone, but they're not forgotten. We've dug up their bones. We've studied their lives. We've reconstructed their ecosystems. We've brought them back, in a sense, through science and imagination. We've learned from them. We've been inspired by them. We've built museums full of their skeletons and made movies about them and written countless books about them. The dinosaurs are extinct, but their legacy lives on. And maybe that's the real lesson here. Not that extinction is inevitable, although it is, but that life persists. That even in the aftermath of catastrophe, even when 99% of everything is dead, life finds a way. The planet recovers. Ecosystems rebuild. Evolution marches on. It takes time. It takes millions of years. But it happens. The Earth has survived 5 major mass extinctions. The end Ordovician, the late Devonian, the end Permian, the end Triassic, the end Cretaceous. Each time, life came back stronger and more diverse than before. And when the next mass extinction happens, life will come back again. Maybe not the same life, maybe not our life, but life. Because that's what life does. It survives. It adapts. It endures. So what happened to the dinosaurs? They died. Quickly, violently, and without warning. They died in fires and floods and starvation and cold. They died because a rock fell from space and happened to hit the worst possible spot on the planet at the worst possible angle at the worst possible speed. They died because the universe is chaotic and indifferent, and sometimes the math just doesn't work out in your favor. But they also lived. For 160 million years, they lived. They thrived. They ruled the planet in a way no other group of animals has before or since. And when they died, they left behind a world that was empty and broken and ready for something new. They left behind the mammals, the birds, the crocodiles, the turtles, all the survivors. They left behind us. And maybe, in some small way, that's a kind of immortality. All right, that's where we're going to end tonight. 2 hours of talking about rocks and death and extinction. Exactly what you wanted to fall asleep to, right? I hope this helped. I hope you learned something. Or if you were already asleep 20 minutes ago, I hope you had good dreams. The dinosaurs are gone, but the story isn't over. It's never over. Life goes on, and so do we. Thanks for listening. Sleep well.